I'd like to thank you all for having me here today to talk about some of the research that we're conducting here at the University of Missouri, specifically in the area of biomedical innovations. Now, the University of Missouri is unique as it is one of only 6 universities in the country that have a med school, a vet school, and a college of engineering all on one campus. So I wanted to talk about what opportunities exist for us to use engineering research to make a difference for both pets and people. My name is Bret Ulery. I'm an assistant professor in the Department of Chemical Engineering here at the university, and we'll be talking about a lot of the work exciting work that's going on here on campus. So one opportunity that exists when you have people coming from many different fields in many different areas is convergence research. And convergence is this idea of bringing together distinct areas to accomplish really wonderful goals and set forth new research opportunities. So traditionally, research has been very multidisciplinary, where people were kind of sticking in their own field. And we think about these kind of, we're an engineering college, kind of cogs that may intersect a little bit, but really are focused in one particular area. So engineering research 100 years ago or 50 years ago might be thinking about how do we have a new chemical process, or how do we manage electricity, and that would fall all within the engineering field. From there, we thought about what happens at those points of intersection, where we might have some overlapping interest and overlapping opportunities. We call that interdisciplinary research. So the opportunity to look at the interface of human and animal medicine, which we call comparative medicine, or biomedical engineering, looking at opportunities that exist between engineering and human medicine. So we definitely can do some research in that area, but it only allows us at those 2 interfaces or 3 interfaces for us to actually do some interesting work. So the new idea is, how do we move to something that's transdisciplinary, where we're all kind of recognizing these big problems are going to take us communicating to one another, that discussion of social data, right? The idea of bringing people together, talking about their research in a way that develops new solutions to large problems. So I think you kind of have to establish what is your ability to speak in this, and I can say that for myself. So I come from a family of very diverse professionals. I'm the son of a mechanical engineer and a hairstylist. My brother works at a retirement home. My wife is a health professional. So the conversations I might have at the dinner table at home tonight are going to be a little different than if I'm hanging out with my mom and my brother. If I start talking technical jargon, they're going to fall asleep at the dinner table. So I have to make sure is, how do I communicate that in a way that's accessible to people coming from different backgrounds? And I actually grew up right next door, within a mile, of Fermilab National Laboratory, one of the Department of Energy laboratories that Prasad mentioned. And there, they've been doing transdisciplinary research for a long time, using their colliders to understand particles and the components that make up particles, and bringing scientists and engineers and people from different backgrounds to accomplish great things. So my educational background has always been, how do we complement, or for me personally, complement chemical engineering with something interesting in the biological or biomedical sciences, and getting those different expertise, including even working for a clinician for one period of time. So when I came to the University of Missouri, I thought, I've got this background, what can we do as far as outreach and creating collaborative networks that do interesting and exciting research? So as I mentioned, when we think about what are we doing research for, we have those opportunities for both pets and people. Well, you kind of say all politics is local. I say all research is a little local as well. My family is made up of our 2 dogs, Colby and Jack. My wife, Dr. Ulery, she's actually a veterinarian and a clinical instructor here, and she wanted me to make sure that she's the real doctor in the family. Me with my PhD, I'm just the other doctor. And this is my family, so I want to make sure that I'm making a difference for both the pets and the people in my family. And I imagine many of you are in that similar boat, that you have pets and people that make up your family. One thing when we think about, and we're maybe focused on the output being human research, is we sometimes tend to forget that along the way there's opportunities to look at research that helps pets, but that also in turn helps people. We have to do preclinical or animal research before we can ever get to those clinical trials. Also, if we work with the veterinarians, they tend to be early adopters of technology. I know I'm a little personally biased on this, but also through my relationships, they tend to be people who say, yeah, let's give it a try. Let's see if it'll make a difference. The regulatory burdens are significantly lower for doing veterinary research. Also, while it might not be as large of a market as you would see with human medicine, it's still large enough that the opportunity to create a solution that makes a difference in that $15 billion market could allow us to get over that death valley that exists for medical products, where we don't have a product out there, but we need lots of money for clinical trials and development and things like that. So if we think about this as not two distinct pathways, but that transdisciplinary approach, we may be able to do some great things, and specifically do them here at the University of Missouri. Now myself, I'm actually a biomaterials researcher, and for biomaterials research, it's really any substance that can be a biological replacement for some sort of bodily function. We could think about traditional ones, maybe you're familiar, things like a hip or knee joint. My mom, just about a year and a half ago, had her hip replaced. She's back playing pickleball, working out a bunch of days a week, back in full function. And that material is designed to carry the weight and support of that particular joint and bone. But there's other materials, things that we could have for like a heart valve that opens under pressure, an LVAD or assist device for a heart. And this could be completely outside of the body, helping for people who are going through heart failure, or even many of you in the audience might be wearing contact lenses. Even those are biomaterials. These biomaterials are comprised of a number of different materials, metals, ceramics, composites, and they've been designed mostly from this idea of replacing some sort of mechanical function, something that'll last for a really long time and something that will not necessarily interact with the body. So because of that, those materials have been developed to be inert, not have a biological function, and actually avoid interacting with the biology. So that's been great for certain things like hip and knee implants, but if we want to tackle grand challenges, for example, maybe we want to develop a new anti-cancer strategy, and it's very difficult to get our drugs delivered to the right cells and the right concentration and carrying that out, or even regenerating tissues, like for a patient who has diabetes, being able to make an artificial pancreas. So the materials that we have available to us don't have the ability to have the effects that we want them to have. So there's this new emerging subfield called biomodulatory materials, where we actually take a step back and design new materials with the physical and chemical properties capable of exerting some interesting biological effects. So I'm going to tell two kind of short vignettes of some work that's going on that brings in these people from different backgrounds to kind of achieve some really interesting and exciting results. So we always want to start with what is a clinical problem we might be interested in addressing. For example, cancer, and specifically hematological cancers, are a pretty big problem. They're made up of three subgroups: multiple myeloma, lymphoma, and leukemia. Multiple myeloma develops in the bone marrow, lymphoma are solid tumors, and leukemia are circulating tumor cells. But they're all kind of under the same basis of immune cell or blood-based cancers. We have about 500,000 new cases that present each year, and about 50,000 of those, about 10%, are leukemia cases in the United States. So that's a pretty big problem for us to try and treat. Now, we might say, okay, that's thinking from the human side. What about from the canine side? Well, canine lymphoma is actually the most prominent cancer in canine patients. And about 30% of all cancers in dogs is of the lymphoma background. And honestly, if your dog lives long enough, it eventually will get lymphoma. So it's a pretty big problem for us to take care of and maybe have some sort of solutions. If your dog gets diagnosed with lymphoma, depending on the type, it has about 6 to 9 months to live. So it's a pretty, and that's with aggressive therapy. And without that, it's only a month or two. In humans, one of the major problematic types of leukemia is acute lymphoblastic leukemia, or ALL. It predominantly affects the young and the elderly. We have kind of an increased rate that occurs for people as they get older. Also, it is the deadliest childhood cancer. Now, the overall 5-year survival rate has improved significantly over the last couple of decades, going from about 10 to 15% only 30 or 40 years ago to now at 70%, which is great, but when people relapse, the survival is very short, only about a 9-month average survival time. And so if we can come up with new solutions that either enhance remission or help treat either primary or secondary cancer, that can make a great impact for these patients' lives. While there are some treatment options available, a lot of them are chemotherapeutic based, which have some significant off-target effects. Essentially, chemotherapy is poison. We just try to poison your cancer cells quicker than we poison your healthy cells. And so in doing that for our kind of adolescent patients, they could have long-term effects even if they are in remission. There's a new therapy that's come out that's about $180,000 to $200,000 in cost, and that's where we're seeing a lot of these new therapies are very, very expensive. So if we can come up with a new one that's effective but also cost efficient, I think we have a really new and exciting game-changing material and product. So we're interested in finding new leukemia therapies. So a collaborator of mine over in the medical school, Mark Daniels, has discovered a peptide or a portion of a protein that has really significant anti-cancer effects. Essentially, he can put a little sequence on it that gets it into different types of cells. And when he does that, regardless if it's T cell or B cell or any of these different types of mouse, canine, or human cancers, it's effective against all of them, which is really exciting. But a lot of times off-target effects is a problem. Luckily for his product, if it gets inside the cell, if the cell's healthy, it's fine. But if it's cancerous, it'll succumb to the therapy. But the problem we have when we work with peptide therapies is they're very difficult to get into cells. They like to break down, they don't pass through the cell membrane. So he was interested in bringing on an engineer who could help them create different types of solutions to deliver that. So what we do is we take a fat and we tether it to our peptide. And when we do that, it actually self-assembles in water, because fats don't like water, but the peptide portion, the protein part, does. So it likes to make these kind of interesting structures, and we can make either spheres or cylinders or worms. And for this application, we made a therapeutic that had the peptide, and it was this nanoparticle that may be able to be better internalized by cells. So we found that we made mostly either short cylinders or mostly spheres. When we exposed cells, we could look at kind of the concentration and kind of how much killing do we get with the more concentration we add. So with the product that Mark had, we saw that, yep, we do get some enhanced killing for both mouse and animal cells. But if we compare that to our product, we get at a lower concentration more death, or at the same concentration, more death as well. So it's exciting that these POSH inhibitor micelles or POSH inhib micelles are better at delivering these to the cancer cells of interest. So at a lower concentration, we can get more death, which is really exciting. But in order to do more work, we need to figure out how to deliver this. So we've been working with a collaborator, Donald Burke, in the biochemistry department, and he has molecules to help us target to the specific cells. So we're kind of building together, kind of Lego pieces, putting those together to kind of have these new technologies that are able to treat cancers. Then we can bring on our veterinary oncologist and our human oncologist to help us make decisions of what elements of the products are necessary in order to move to clinical trials. From there, what we're interested is not only trying to treat the cancer that's there, but to prevent cancer from happening again. So if we kind of take this technology and we're able to treat the cells, possibly if we co-deliver some other factors, we might be able to prime the immune system to protect against having cancer flare up again. And if we do that, that could enhance remission. So there's opportunities to even build on this first platform into something new and exciting. So if we think about this opportunity to kind of prime the immune response, you might be familiar with things called vaccines, right? And vaccines are essentially the greatest thing that we've come up from for a human health standpoint. And we give you a portion of some sort of disease in a way that should allow you to be able to see it and then prevent it from happening again. So since the late 1700s, when the first vaccine was developed by Louis Pasteur against smallpox, there's been a number of great successes with a lot of different diseases, including diphtheria and polio and measles and all these things that were significant banes to human health, and we've been able to come up with great solutions for that. Now, if you think about it, so the way a vaccine works is if in a population where people aren't vaccinated, once somebody gets sick, they spread it to everyone else, right? The common cold. Once somebody gets it or your kid gets it, everybody at daycare gets it, right? Now, if we have a vaccine, if most of the population is protected, then we have what's called herd immunity. So it prevents that spread from people to people and getting out there quickly. And even some people might not be able to be vaccinated. Maybe they're immunocompromised, or they've had cancer recently, or they're too young to get the vaccine. So if we are able to vaccinate the population, we can make a big difference. Now, when vaccines were kind of in their heyday, with the polio vaccine coming out in the early 50s, people were standing in line waiting to get their kids vaccinated because of all the problems that are associated with polio. Well, we maybe forget some of those lessons of how bad some of these diseases are, as we have people now who see vaccines as kind of the evil clown that lurks trying to get at your kids. But really, vaccines have amazing potential, and we need to think about them again in what they're capable of doing and the type of things that they prevent. So when we think about how we create a vaccine, there's a couple of different ways that we can do this. We're always inspired by the disease itself, whether it's a bacteria or a fungus or a virus or even cancer. And when we do that, we have to think about what are some ways that we can expose you to that pathogen without giving you the disease. First thing we can do is we can kill it. So we can use radiation or heat, and we can inactivate that whole pathogen. So the advantages of that is it's safe, and it's easy to transport because it's dead. But the problem is that you've got to make sure you kill it. Even if 1 in a million is still alive, that could still cause an infection. Also, because it's dead, it doesn't always necessarily give the same type of response that a live microbe would. Now, another thing we could do is we could attenuate it. So we could do some sort of genetic manipulation in the lab, take out some of its virulent mechanisms, and allow us to have a living pathogen, but with reduced virulence. So that would be like the flu vaccine is done that way. So the advantages is you're seeing a live organism, but it doesn't have all the ability to cause disease, and it does give a durable response. But the problem is that if those genes change back, you could get something that's very virulent. Or for people who are immunocompromised, if the genes are just dampened and not actually knocked out, it could still cause disease. So the new area and kind of exciting new approach in vaccine research is to just look at subunits. So this is where we're not looking at the whole pathogen, but just little portions of it that we actually build our immune response to. So if we can go ahead and develop new solutions that are capable of just focusing on that, that would be really exciting. So it's obviously much safer. We don't have all this other bacterial or viral crud, but at the same time, they're very weak. So we need to come up with new solutions that can kind of enhance the immunogenicity of this product. So we work with that same Micelles technology that I mentioned earlier, that's kind of this self-assembled lipidated peptide. And we went ahead and vaccinated animals with a couple of different structures. So we wanted to see if structure played a role in the vaccine response, so we could make nanoparticles that were somewhat kind of spherical or clusters or these long twines or even braids. And what we figured out with that is that structure matters. So we can play around and figure out if we want to induce an immune response or prevent an immune response, we can change our nanomaterial structure. And working with some of our collaborators, we've been able to now think about new ways to implement this. The first is to work with another engineering professor, Dong Xu, who I think got mentioned in Prasad's talk. He has a system to kind of find new vaccines for us to utilize. So he can computationally do medium data, maybe not big data, and find some of these products for us to try. And then we can work with our collaborators like Jeff Adamvich, who's a microbiologist over in the vet school here, to look at different types of bacteria of interest. And what we can see is that collaboration, we started with thousands of different products and got it down to 10 and then 5 peptides, vaccines that we could try, and when we vaccinated, we found one that worked. So instead of having to try and vaccinate thousands of mice with thousands of different products, we were able to get that down to a very small amount by talking among one another and having that transdisciplinary research approach. And now we're going to apply that for trying to do tick vaccines to prevent against Lyme disease and other tick-based vaccines, and then also influenza with collaborators in the vet school and the med school. So as I mentioned, MIZZOU has a significant advantage. We are one of only 6 universities that have those colleges, those unique colleges on one campus. We have researchers here who are passionate about this transdisciplinary approach and the collaborative research that's available. We're working to build a network of biomaterials researchers who fit within these different areas through this Biomedical Innovations in One Health Materials, or BioOM. And then we're also working on this new exciting translational and precision medicine complex that will house researchers from these different colleges doing great collaborative research in this area. So I think MIZZOU is really set and well supported to conduct research at this transdisciplinary area. All right, thank you.